How did the United States plan to arm a rapidly expanding military in December 1941? Existing manufacturing facilities simply failed to output enough Thompson submachine guns. The M3 entered the Second World War without polished walnut stocks or the visual authority of traditional firearms. Ordnance engineers designed it strictly for close-quarter combat. Total wartime mobilization demanded millions of individual small arms. The national population stood at roughly 133 million citizens. Supplying a drafted ground force of that massive scale meant permanently abandoning outdated production techniques. The Thompson submachine gun required traditional gunsmithing. Factory operators secured solid steel blocks onto heavy milling machines. The high-pitched screeching of rotary cutters shearing through metal filled the production floors. Each internal component demanded extensive manual fitting by skilled labor. Final assembly crawled. One completed weapon consumed excessive volumes of high-quality ordnance steel, leaving behind heavy piles of discarded metal shavings. Precision machining became a vulnerability. Global logistics demanded volume. Complex firearms created a logistical dead end during multi-front campaigns. The government invoice for every manufactured unit stood at $200. The demands of October 1942 forced a rewrite of United States artillery and ordnance production standards. Battlefield analysis from the European theater compelled military strategists to abandon traditional milling processes. Planners observed weapons like the German MP-40 and the British Sten across multiple combat zones. The British Sten cost less than £3 to manufacture, providing an immediate tactical advantage. These designs ignored traditional gunsmithing aesthetics in favor of stamped sheet metal and basic welding. The solution required bypassing specialized firearm lathes and utilizing civilian automotive stamping presses instead. In October 1942, the Army issued formal requirements for a new submachine gun reflecting this industrial shift. The specification mandated the standard .45 ACP caliber to ensure logistical compatibility with existing ammunition stockpiles. The government bypassed traditional arsenals and awarded the manufacturing contract directly to the General Motors Guide Lamp Division in Anderson, Indiana. Before the war, this specific factory specialized in fabricating civilian automobile headlights and chrome bumpers. Their heavy mechanical presses proved perfectly calibrated for striking thin sheet metal into precise weapon components. Heavy hydraulic presses stamped two flat steel blanks into identical cylindrical halves in seconds. Assembly workers fused these shells together, and bright sparks from arc welders illuminated the factory floor. Operators then installed a basic heavy steel bolt inside the hollow welded casing. The resulting firearm fired roughly 450 rounds per minute. Automotive engineers solved the military supply bottleneck by prioritizing production volume over craftsmanship. The United States military officially adopted the weapon into service in December 1942. What did the output of automotive engineers look like? The M3 submachine gun lost all wood and traditional lines. General Motors delivered a product that defied past infantry expectations. No polished walnut, no heavy machined steel. Instead, a bare skeletal frame emerged for World War II combat. The weapon featured a simple cylindrical receiver and a rough retractable wire stock. Industrial mass production erased conventional firearm aesthetics. Cost fell to $20. The stark metal tube closely resembled standard hand-pumped lubrication equipment. Frontline troops equated the new weapon to auto shop tools, naming it the grease gun. Why did a primitive weapon prove effective against Japanese troops? Dense canopies and coral bunkers reduced engagement distances to a strict minimum. The stamped skeletal construction bypassed stateside armories and shipped straight to the Pacific Theater. American forces advanced through layered island defenses at contested locations like Peleliu. The Japanese military established hidden firing zones and narrow connecting corridors deep inside the natural coral rock. Combat operations routinely occurred at close ranges of less than 30 meters. In these unpredictable firefights, the submachine gun operated at a deliberate rate of 450 rounds per minute. This steady mechanical rhythm prevented infantrymen from draining their 30-round magazines during sudden ambushes. The stamped metal frame offered greater mobility inside confined cave networks compared to standard long-barreled rifles. It provided immediate suppressive firepower without the heavy burden of wooden components or complicated field maintenance routines. Traditional combat expectations collapsed. How did engineers simplify the firing cycle? They entirely removed the barrel locking mechanisms. Shifting production contracts to the heavy automotive sector dictated a new approach. The design mandated a straight blowback system housed within a stamped steel receiver. General Motors engineers optimized the weapon around an open bolt configuration. The operator pulled the charging mechanism rearward. A distinct metallic clank sounded as the massive bolt locked into the rear steel sear. The trigger released the spring tension. The heavy steel block drove forward. It stripped a .45 caliber cartridge from the magazine. It chambered the heavy round. It fired instantly. Expanding powder gas forced the block backward against the dual guide springs. The spent casing ejected. The cycle reset. This linear layout eliminated gas tubes and rotating components. Dirt and moisture found no grip inside the mechanism. The open chamber allowed continuous air circulation, cooling the barrel during prolonged combat engagements. The massive bolt directly restricted the firing tempo. The older Thompson submachine gun delivered 700 to 800 rounds per minute. That speed depleted 30-round ammunition supplies in seconds. The heavy mass of the new steel block intentionally slowed the internal mechanical rhythm. This reduction represented a calculated engineering decision for battlefield control and ammunition conservation. Soldiers maintained consistent accuracy by firing short bursts instead of firing uncontrollable streams. The fire rate was capped at exactly 450 rounds per minute. 30 heavy rounds, 1 detachable magazine. The .45 ACP caliber stopped targets instantly. Production demanded maximum speed. General Motors Guide Lamp Division took control. Traditional weapon milling consumed entire days. Stamping steel panels cut production to hours. Heavy industrial presses shaped the parts. Workers welded the two halves together. Hot sparks flew. A simple cylindrical housing formed quickly. Heavy internal components rode on basic guide rods. Recoil springs absorbed the heavy shock. Soldiers replaced broken springs in seconds. But by late 1944, combat exposed a critical flaw. The protruding external handle failed. Rough field conditions destroyed the lever daily. The design demanded an urgent overhaul. Then engineers fixed the weak handle issue. The M3A1 arrived. The revised design eliminated the lever. A simple drilled finger recess appeared. Operators manually pulled the heavy bolt backward. Time was short. The missing handle simplified factory assembly operations. The modification removed the primary breakage point. The thick wire stock collapsed inward. Overall length dropped to 22 inches. Confined spaces demanded maximum weapon compactness. The Ordnance Department distributed the modified automatic weapon to elite paratroop divisions and mechanized armored vehicle crews across the European theater. Why did traditional infantry tactics fail on the remote islands? Japanese engineering networks forced instant point-blank engagements. The ultra-compact physical dimensions of the updated M3A1 submachine gun perfectly matched the geographical barriers of the Pacific theater. A combat engineer advanced slowly along a narrow jungle trail. Concealed firing positions remained invisible inside hollowed rock formations until the first muzzle flash. Sudden hostile contact demanded immediate suppressive automatic fire from the hip without utilizing standard iron sights. Deep coral trenches and vertical limestone walls severely restricted the physical handling of standard service rifles. Japanese defensive systems relied on fortified coral ridges and subterranean infrastructure. On the island of Peleliu, military engineers excavated several kilometers of interconnected tunnels within a single square kilometer of surface area. These subterranean defensive networks negated the standard American advantage of distant artillery coordination. Combat units operated inside enclosed physical environments where visual range rarely exceeded 15 meters. The short weapon allowed infantrymen to clear confined passages without exposing their silhouettes to return fire. The heavy .45 ACP cartridge delivered maximum kinetic transfer at these compressed tactical ranges. The heavy bullet reliably penetrated dense jungle vegetation. How did primitive stamping break the Imperial Japanese Army rhythm? Dense automatic fire rendered bayonet charges impossible. In the Pacific tropics, wide weapon clearances collided with traditional infantry tactics. The Japanese military command relied on discipline. Officers emphasized endurance. Strategy prioritized individual resolve. Soldiers executed aggressive maneuvers. The manuals demanded closing the distance. Troops moved fast. They exploited uneven terrain. They relied on bolt-action rifles. The Arisaka Type 99 fired a 7.7mm cartridge. The rifle measured over 1 meter long. A fixed bayonet added 40 centimeters. The weapon functioned well in open terrain, but Pacific Islands offered no open spaces. Peleliu featured dense coral ridges. Visibility dropped to near zero. The Japanese rifle required manual cycling after every shot. The soldier fired. Bolt pulled back. Brass ejected. Bolt pushed forward. Action locked down. The practical firing rate peaked at 15 rounds per minute. The battlefield rhythm remained deliberate. Brief bursts of movement, sharp pauses, single shots. The American submachine gun broke this sequence. The weapon operated from an open bolt. It delivered 450 rounds per minute. One trigger pull, no crew support required. No complex positioning needed. The sensory contrast dominated the jungle. A single Type 99 crack met the continuous M3 roar. Tropical conditions ruined complex firearms. High humidity caused rapid corrosion. Coral dust locked tight metal surfaces. Standard tolerances for military rifles measured in fractions of a millimeter. But the American weapon featured huge design gaps. This specific detail prevented jamming. Thick mud entered the receiver chamber. It simply dropped out through oversized clearance slots. Sand grains passed through the mechanism. The heavy bolt kept reciprocating. Firing never stopped. American troops saturated confined spaces. Thick vegetation offered zero protection. Japanese soldiers advancing inside reinforced earthworks faced massive fire density from American submachine guns. A manual rifle could not suppress this firepower. Stamped steel overcame individual resolve. The operational reality changed. Combat distance shrank to meters. Why did Japanese field reports isolate trauma from American submachine guns? The .45 ACP cartridge transferred maximum kinetic energy at ultra-short distances. Weapon reliability allowed continuous fire. Counterattack stalled immediately. Japanese Type 38 rifles utilized 6.5mm ammunition. They pierced targets cleanly. The American bullet diameter measured 11.43 millimeters. A 230-grain projectile struck with blunt force. Inside concrete bunkers, mechanics dominated. A soldier pulled the trigger. Heavy rounds dumped energy into targets. Japanese field surgeons documented severe tissue trauma from automatic fire, noting a sharp contrast with typical bolt-action wounds. The psychological effect matched the ballistics. The M3 cycled at 450 rounds per minute. The cadence was slow. Rhythmic impacts echoed down underground coral corridors. Acoustic pressure disoriented defenders. Infantry could not communicate. The noise masked all movement. Japanese arsenals faced critical raw material deficits. Steel output dropped below 2 million tons. Zero fuel remained. Production collapsed. The .45 caliber advantage exposed a wider macroeconomic reality. The submachine gun embodied American manufacturing scale. Japan hoarded scrap metal. Deficits grew. United States mills cast 80 million tons of steel annually. This volume altered military procurement. Designers made the firearm expendable. It was cheap. It was replaceable. Factories reproduced it endlessly. Supply chains saturated the front. Japanese forces conserved every cartridge. American units traded stamped metal for territory. Tactics failed. Volume dictated battle outcomes. Japanese infantry confronted a stamped metal firearm designed explicitly to nullify their tactical skill through sheer production efficiency. How did a wartime weapon remain active during conflicts in Korea and Vietnam? Its efficiency was measured exclusively by the simplicity of mass replication. The principle of manufacturing efficiency did not vanish after the Japanese surrender in 1945. American supply networks carried the hardware into the Korean War. Urban combat demanded compact firepower. Infantry units cleared ruined buildings block by block. The mechanism required zero complex maintenance. Combat troops deployed it in massive numbers across the rugged peninsula. Operations later shifted to the dense canopies of the Vietnam War. The stamped steel receiver proved its worth. It resisted thick mud. It withstood constant jungle humidity. Moving parts kept cycling smoothly even when subjected to severe environmental exposure and continuous daily combat. Engineers completely abandoned aesthetic refinement. They prioritized pure production volume. Factories stamped sheet metal instead of milling solid steel blocks. Industrial optimization permanently replaced traditional craftsmanship. Over 600,000 units rolled off the assembly lines, proving that raw manufacturing scale easily outweighed traditional mechanical complexity. This output established a permanent standard for American military supply across Asia. Cold War engineers adopted this exact production template. This approach directly defined the architecture of post-war assault rifles. Veteran reports recorded trench fear. Today, historians evaluate the M3 differently. It indicates pure production warfare. The combat path ran from the Pacific Islands to Vietnam. It locked in a new infantry metric. Tactics shifted. It neutralized enemy defensive advantages. Courage meant nothing. Survival relied strictly on mass-produced firepower. World War II became a contest of industrial capacities. The M3 converted factory output into fire suppression. General Motors stamped thousands of sheet metal receivers. The weapon became a disposable battlefield tool. Zero field repairs. Costs dropped. No engineering aesthetics. Its sole function was instant firefight termination. $20 per unit forever altered global infantry warfare standards.